Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematical sciences. In this session, we shall deal with flow in a network problems. In particular, we are interested in finding maximal flow problems and maximal flow and Mincut theorems. Finally, by making use of this maximal flow Mincut theorems, we are going to construct a maximal flow for a given network problems. So, the first idea is maximal flow problems. What is a maximal flow problems? A maximal flow problems is described as follows. It is a problem of shipping a homogeneous product which is stored in one place, which we called as source. From source to a particular destination we called as sinks. So, a maximal flow problem is nothing but problem of shipping a homogeneous product from a specified point to a particular destination. Before study about this problem, let me introduce the notation and certain basic definitions involved in this maximal flow problem. The first notation is Fij. Fij is flow in the arc ij. So, in the arc, if we consider this arc which has a node I and node j, the flow in this arc is denoted by Fij. So, which is the quantity shift from node I to node j. So, Fij is the quantity shift from node I to node j, which we say those things as flow in the arc ij. The next notation is F. F is the total amount shift from the source to sink. So, your total amount shift from source, we call source as S and sink as N. The total amount transported from the source node to sink node, that will be denoted by F. So, F is the total amount shift from source to sink. The final notation is Kij, which is the capacity of the arc ij. This is our arc ij. For this arc ij, the capacity is denoted by Kij, which is the maximum flow possible from node I to node j. From node I to node j, the maximal flow possible is called as capacity of the arcs. So, in a maximal flow problem, Fij is the flow in the arc ij, F is the total amount transported from source to sink, and Kij is the capacity of the arc ij. With this notation, the next definition is conservation. What we mean by conservation is the total flow into a node must be equal to the total flow out of that node. So, if a particular node k is there, then the total flow into that node should be equal to the total flow out of that node. So, if we name this flow as Fij and this is Mij, then if Mij equal to Fij, then we say that this flow is satisfies the property conservation. So, a conservation means total flow into a node must be equal to total flow out of that node. With this notation and definition, now let us consider a network problem. Unlike in transportation problem, in maximal flow problem, there is no direct arc from source to sink. There is some intermediate node between source and sink. If we consider this network diagram, here the node S is our source node and the node N is our sink node, and certain nodes in between source and sink, which we name it as node 1 and 2. These are called intermediate nodes. So, our network consisting set of nodes S 1, 2, N, in which S is the source node and N is the sink node, and these two nodes 1 and 2 are called intermediate nodes. Now, if we consider this arc S1 and if we put this arrow mark, this is a directed arc from node S to 1. So, if we consider this network diagram, then this is a directed network diagram. Here the arc S1 is a directed arc, the arc S1 is a directed arc in which it carries a flow Fs1. Fs1 is the amount shipped from node S to node 1, that is called Fs1. Suppose if we name the capacity of this arc Ks1, the capacity of this arc S1 is Ks1, then this flow Fs1 for the arc S1 should be less than or equal to capacity of this arc. So, for the arc S1, the flow from node S to node 1 should be less than or equal to the capacity of that arc S1. Now, if we consider this arc, which will be arc 1n, which carries a flow F1n, whose capacity of this arc is K1n, then obviously F1n should be less than or equal to K1n. So, in this network diagram, we have 4 nodes in which S is the source node, N is the sink node, these two are intermediate node. Each and every arc carries certain flows whose capacity also given. Now, our aim is to determine maximum flow which flow from the source node S to sink node N. Our aim in this problem is this one. Consider the flow network in the above figure. So, a flow network is given. We will consider the flow network as a directed graph. So, we have the following network. Consider this network problem. Given the capacity Kj on flows on each arc Ij, which satisfies the conservation. So, this network diagram, for each arc there is a capacity Kj and flows are there, that flow should satisfy the conservation. That means, the total flow into a particular node should be equal to the total flow out of that node. Now, the question is, determine the maximum flow F that can be sent from source node S to sink node N. So, now our problem is, we have to find the maximum flow F that can be transported from the source node S to the sink node N. So, our aim of this problem is, we are interested in finding the maximal flow from source node S to the sink node N. That is our problem. Before solving this problem, let us discuss about certain basic definitions, then we will try to solve this problem. First, we convert the problem into a linear programming problem. For that, consider the networks. It is a directed networks. So, consider this network. Now, we try to form a linear programming formulation for the given network problem. Now, we consider the source node. For the source node, first we have to check the conservation property. Before that, our aim for this problem is maximum Z equal to F. Our aim is to find the maximal flow from this source node to the sink node N. Therefore, our objective is maximum Z equal to F. Now, which satisfies certain constraints, we will list out constraint one by one. First, we will consider the source node S. For the source node, first let us construct a constraints of conservation. Now, the total flow into the node is F. and the total flow out of that node is, this is the total flow out of that node and this is the total flow out of the node. This flow of the arc S1 is denoted by Fs1, and if we consider the arc S2, their flow is Fs2. So, the first constraint for the source node S is Fs1 plus Fs2 equal to F. Now, let us construct a constraint for the sink node N. For the sink node, the total flow out of that node is F, therefore, F. Now, the total flow into that node is the flow from the node 2 to N and the flow from node 1 to N. Therefore, the constraint is F1N plus F2N equal to F. So, as far as the sink node constraint, the constraints for the conservation is F1N plus F2N equal to F. Now, we have two intermediate node, node 1 and node 2. For those two nodes, we will try to put a constraints in terms of conservation. If we consider node 1, for node 1, the total flow into that node is, one is from node S, which is Fs1, another one is from node 2, which is F21. So, the total flow into that node 1 is Fs1 plus F21. Now, for the node 1, the total flow out of that node is flow from 1 to N and flow from 1 to 2. So, flow from 1 to N, which is F1N, and flow from 1 to 2, which is F12. So, as per conservation property, Fs1 plus F21 equal to F1N plus Fn2. The same way, for the intermediate node 2, we can put a constraints in terms of conservation, which is nothing but from node 2, the flow out of that node is F2N and F21. So, F21 plus F2N, and the total flow into that node is F12 and Fs2. So, Fs2. So, these two constraints for the conservation constraint for the intermediate node, this constraints for the source node, this constraints for the sink node. Now, the flow in each arc, the flow in the arc Fs1 should less than equal to capacity of that arc S1, which is Ks1, which should be a non-negative. The same way, we can, for the arc S2, the flow is Fs2 should be less than or equal to Ks2, should be greater than or equal to 0. Then, for the arc 1N, F1N, the flow F1N should satisfy Ks1 and should be greater than 0. The same way, for the arc F2N should less than or equal to K2N and greater than or equal to 0. The same way, we can write F12 should be less than or equal to K12 should be greater than or equal to 0, and F21 should be less than or equal to K21 and it should be a non-negative quantity. Now, these 6 constraints put restriction on flows on the network so as to be non-negative, Fs1 greater than 0 and have an upper bound each Fsi less than or equal to Ksi. So, the given network problem can be converted into a linear programming problem. The corresponding linear programming problem is maximum z equal to f subject to the constraints Fs1 plus Fs2 equal to f, F1n plus F2n equal to f, and Fs1 plus F2n equal to F1n plus F12. The same way these equations. The first constraints corresponding to source node, the second constraints corresponds to sink node, and these two constraints for the intermediate node, and these set of 6 constraints are the constraints or restriction on flows, which is to be a non-negative and have an upper bound. Now, the given network problem can be converted into a linear programming problem. Now, by solving this linear programming problem using simplex method, we can get the maximal flow for the given network problem. By solving this linear programming problem, we can get a maximal flow for the given network problem, but there are some efficient method than this method is available in the literature. Now, let us discuss about those methods first. In order to discuss those methods, first let us discuss about certain basic definitions. The first definition is cut. Let n denote the collection of all the nodes in the network. Then a cut separating source and sink is a partition of the nodes in a network into two subsets S and S bar, such that source node is in S and sink node is in S bar. So, a cut separates the collection of all the nodes of a given network diagram into two sets S and S bar. So, a cut is denoted by S bar in such a way that the source node is in S and sink node is in S bar. So, mathematically S bar is said to be a cut if it satisfies the following condition: S union S bar equal to collection of all nodes of the given network diagram, and S intersection S bar should be an empty, and the source node is in the set S and the sink node, which is N, should be in S bar. So, mathematically S bar is said to be a cut if it satisfies the following condition: S union S bar equal to N and S intersection S bar equal to empty, source node is in the set S and sink node is in the set S bar. Once we know the definition of cut, the next idea is capacity of a cut. The capacity of a cut is denoted by KS bar, is the sum of all the capacity of the arcs from the nodes in S to those node in S bar. So, a capacity of the cut, if S bar is a cut, its capacity is denoted by KS bar, is nothing but sum of all capacity of the arc from nodes in S to those nodes in S. So, in order to compute the capacity of the cut, first you have to collect all the arc which has source node in S and the N nodes in S bar. So, you have to collect all arcs from S to S bar. Then, if we sum the capacity of all the arc from S to S bar, which will gives us the capacity of the cut. So, for a given network diagram, a number of cuts are available. Now, among all cut, any cut with the smallest capacity is called minimal cut. So, a minimal cut of a given network diagram is nothing but a cut with smallest capacity. So, a cut with smallest capacity is called minimal cut. With this definition of cut, capacity of cut and minimal cut, next we will discuss about two basic results. The first result is, for any directed network, if F is the flow from source to the sink and SS bar is any cut, then the value of F is less than or equal to capacity of the cut KSS bar. So, in short, the result says that for any directed network, the flow from source to sink, that is F, should be less than or equal to the capacity of any cut KSS bar. So, this is our first result. The second very important result is Maxiflow Mincut theorems. Maxiflow Mincut theorem, which says that for any network, the value of the maximal flow from source to sink is equal to the capacity of the minimal cut. So, the Maxiflow Mincut theorem says that the maximal flow from source to sink, which we denoted by F, the maximal flow from source to sink denoted by F, it should be equal to the capacity of the minimal cut. Suppose our SS bar is a minimal cut and its capacity is K, then the Maxiflow Mincut theorem says that the maximal flow from source to sink equal to capacity of the minimal cut. So, with the help of these two results for a given network diagram, we can easily find out the maximal flow. For that, consider the given network. Consider a directed network. So, we have this network which has source node S and sink node N, two intermediate nodes. Now, let me explain what we mean by cut and minimal cut. So, for this network diagram, a many number of cut is there. Now, if we consider this one, if I take this as one cut, so this will be denoted by S and this will be denoted by S bar. So, if you consider this cut, here our S is source node S and two intermediate node 1 and 2, and S bar is the sink node N. So, for this network, if S equal to set S12 and S bar equal to N, then this is one cut, we name this cut as SS bar. Now, the associated arc in this cut is S to N is not possible, because there is no arc from S to N, therefore, S to N is not possible, whereas 1 to N we can associate arc, because since there is an arc between the node 1 to N, the associated arc is 1 N. Similarly, one more associated arc is 2 N. Now, if we consider these two arcs, here the first node is in the set S and the second node is in the set S bar. So, for this cut, the associated arc is 1 N, 2 N. Now, in this associated arc, I am not including the arc S n. The reason is, from the node S to the node N, there is no arc. Therefore, in this associated arc, we have arc 1 N and 2 N. Now, for this cut S S bar, we have only two associated arc 1 N, 2 N. Now, the capacity of this cut K S S bar is nothing but sum of all arc from the set S to S bar. So, here one arc is K 1 N. So, its capacity is K 1 N, and the second associated arc is 2 N, its capacity is 2 N, K 2 N. So, if you sum it, K 1 N plus K 2 N, which is the capacity of the cut K S S bar. So, if we consider a cut which consisting S equal to S 1 2 and S bar equal to N, then the capacity of that cut is K 1 N, K 2 N. Now, if we consider one more cut for this problem, suppose if I consider this as my cut. So, I will take this as my set S and this is my S bar, where S is consisting the nodes S and 2 and S bar is consisting the nodes 1 N. So, we consider a cut S S bar, where S equal to set S 2 and S bar equal to set 1 N. Now, for this cut S S bar, what are all the associated arc? The starting point should be from S and ending point should be in S bar. So, first we will take the node S. From S, there is a arc, directed arc is there to node 1, which is S 1, there is a arc. Therefore, this node has an associated arc S 1 is there. Then there is no arc, directed arc from S to N is there. Therefore, there is no associated arc from S to N. Next, 2 to 1, suppose if we consider the network as this way, directed network, then 2 to 1 there is a directed arc, 2 to 1 there is a directed arc, 2 to 1 there is a directed arc. Therefore, we can include the arc 2 1. Next, there is a arc between the node 2 to N, therefore, we can include 2 N also. So, for this cut, the associated arc is S 1 and 2 1 and 2n. These are the associated arc. Now, if you for all this associated arc, if we sum the capacities for this arc, the capacity is Ks1, for this arc the capacity is K21, for this arc the capacity is K2n. If you sum all the capacity of associated arc, which will gives the capacity of the cut Ks bar. In the same way, we for given network diagram we can find many cuts. For each and every cut we can compute the capacity. Now, among all capacity of the arc, whichever cut has a minimal capacity, that is called minimal cut. So, among all cut of a given network diagram, any cut which has a minimal value, that minimal value is called minimal cut. Now, by making use of Maxiflow minicut theorem, in order to find the maximal flow between any two nodes of a network, it is enough to find the capacity of the minimal cut, because Maxiflow minicut theorem says that the maximal flow from source to sink is equal to the capacity of the minimal cut. F, which is a maximal flow from source to sink, is equal to capacity of the minimal cut Ks bar, where S bar is a cut which has a minimum capacity value. Now, with the help of this Maxiflow minicut theorem, we can find out the Maxiflow for a given network diagram. Consider the problem. Using Maxiflow minicut theorem for the network given below, compute the Maxiflow F from S to N. So, for a given network diagram, it is a directed network. Consider this network. For this network, our source node is S and our sink node is N. We are interested in finding the maximal flow from S to N. In order to find maximal flow from S to N, it is enough to find out the minimal cut value, the capacity of the minimal cut value. For that, for the given network diagram, we list out all the possible cuts. Then for each and every cut, we try to find the capacities. Then among all capacities, we choose the minimum. That minimum value is the minimal cut value of the given network diagram. That minimal cut is the capacity of maximal flow of the given network diagram. For this network diagram, we have these 4 cuts. These are the only 4 possible cuts. Now, for this cut, if we consider the associated arc, we have a associated arc is 1n and 2n. Therefore, the capacity of this cut is 9 plus 8. So, capacity of this cut Ks bar equal to 9 plus 8, which is 17. The same way, for this cut, if we calculate the capacity, which will be 7 plus 9, 16. Now, for the third cut S1 and S bar 2n, the capacity is nothing but 9 plus 3 plus 9, 21. Now, for the final cut S2 and S1, the capacity is from S2 we have S1 is there and another arc which is 2n is there. Therefore, for this cut the capacity is 7 plus 8, 15. Now, this network diagram has only 4 possible cut. Among all cut, the final cut has the minimum capacity which is 15. Therefore, for the given network diagram, the minimal cut value is 15. Now, by Maxiflow minicut theorem, the maximal flow of a given network diagram is nothing but the value of minimal cut. So, here the minimal cut value is 15. Therefore, the given network diagram, the maximal flow is nothing but 15. Let me recap. The capacity of a cut is denoted by Ks S bar, is sum of all capacity of the arcs from node in S to those in S bar. A cut with smallest capacity is called minimal cut. For any network diagram, the flow from source to sink should be less than or equal to the capacity of the cut. Now, for any network diagram, the maximal flow from source to sink should be equal to the capacity of the minimal cut. Question: using Maxiflow minicut theorem for the given network diagram, find the maximal flow. Thank you.